Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is part B of subsection 551. We just talked about making an adjacency matrix for a digraph and thought of it as a map that answers a question. A map from, now this is a map from Z4 to Z4, so that means like in this case, we're working with a digraph with 4 vertices, and the 4 vertices themselves give standard basis elements here of z cross z cross z cross z, which is so tuples with integer integer entries in each component. And so these are 4 tuples. So it was a question dealing with a collection of vertices with some multiplicities on them, and we output an answer, and the answer has to do with number of paths leading into vertices, or leading into a collection here that we have, and that would be the solution. So we have a Z-module map represented by the adjacency matrix. Now, what happens if we run the adjacency matrix as a map twice? So we compose it like we run the map once, and then we run it again afterwards. So the adjacency matrix itself answers the question for paths of length 1. Now, if we answer the question for path of length 1, and then we put that answer into paths of length 1, again, what we end up getting is paths of length 2. So we've answered the question for paths of length 2. So quite literally, if we want to get paths of length 2, we can get a matrix as follows. We look for paths of length 2 that come into 1 from the various vertices, paths of length 2 that come into 2 from the different vertices. This would be f of, so because f of f as a function actually counts paths of length 2 coming into each thing. And so to find the matrix, you would just simply find the image of 1 as a column, 2, 3, 4. We just answer the question for paths of length 2 in turn. And if we did that, we'd get something like this. Let's take a look and actually run through that computation by looking at the graph. Okay, so here's the digraph. And let's think. For vertex 1, what do we have coming into vertex 1? That's going to be in the first column here, because it answers the question for that one vertex. What are the paths of length 2 coming into that one from the various destinations? First, from 1 itself, is there anything that has length 2 that comes into 1? Well, right here, so we have this one and then that one. See that? That's a path of length 2. We could also go here and then follow this one. That's another path of length 2. Those are the only 2 paths of length 2 that come into 1, and they both come into 1 from 3. So we have, from itself. Sorry, from itself. So 1. So coming in from 1, we have 2 paths coming into 1, 2, 1. All right. And then let's see. Now, what about coming in from 1 from 2? There's nothing. Coming in to 1 from 3 of length 2. Let's see. No, every time we get length 2, we're always, see here, because 3 doesn't have any arrows going any other places. So yeah, so that there's none. What about from 4? Going to 1 of length 2. Well, we could go here to here, and then there. That's 1. And we can go here, there, and then there. So here like that, or here like that. That looks like there's 2. Coming from 4. Yeah, I mean, if we went this way, that would just add an extra 1. There's 2. So it looks like coming from all the different vertices to the vertex 1, we get 2, 0, 0, 2. let's take a look at that and compare it to what we have down below. So for the for f of f, let's see. So we had f of f, and we have right here 2, 0, 0, 2, just like that. Okay. So we confirm that. And if we work through the similar process for all the other ones, we'd have these as well, these different images coming into it. Now, this is the same. So now what is this? This is the same thing as quite literally answering the question of paths of length 2. So first answer the question for paths of length 1, then throw that answer into the paths of length 1 question again, and we end up getting this. So we kind of double back a couple times and we get this. So it's like we evaluate this, and then we okay, so right. Okay. Let's see what I have. So we have the adjacency matrix. So we output this, right? Then we take this and we put it into the adjacency again to go back another path. And then we end up getting this one. So we can actually use matrix multiplication in order to get this guy. So each column. So this column is obtained by taking the first column of the adjacency matrix itself and then plugging it into this map. So the first image of the adjacency matrix, put it as an input, and then run the map again, and we get that column. And in a similar way, we get all the other ones. So to get this one 3, 0, 0, 3, what would we do? We would take okay, so we take the image of the second guy of the second vertex, which is this, and we throw that in as the input. So this 3, 0, 0, 0 would now become the input here, and then multiply, and then we'd end up getting this 3, 0, 0, 3. And similar for these other ones. In a sense, you can call that process of doing that matrix multiplication between two square matrices, a 4 by 4 times a 4 by 4 times itself, and end up getting an a squared. Essentially, what are we doing? We're just taking the columns. So it's like we're multiplying this matrix by itself. Let's write that out, actually, so you can kind of see what's going on. So what we're doing is we're taking this matrix times itself. So if you want for a minute, let's just kind of write out what that would look like. 0, 0, 2, 0, 3, 0, 0, 0, 1, 0, 0, 1, and 1, 0, 0, 1. So we take this matrix times itself, and let's just kind of ignore everything else for a minute. So how do we do this? Well, basically what we do is we take this and we multiply it to that, and we get a result. And that result is what goes right here. So all this times that goes right here. Now what goes right here is this result times all that. And that goes right there. Then what goes right here? This times that result. So we put this in to there, and we get that guy, and then we put this into that function, and then we get that guy. It's a composition of functions, because what does this do? So what is this? This is the image of the first standard basis element. So take that image and then run it out, and then of this particular map, and then run it into the next map to get the image of the first standard basis element via the whole composition. So this is the ultimate image after running the map twice. So we can just get column by column in this way by just throwing this one in here, getting that guy, this one in here, getting that guy, this one in here, getting that guy, this one in here, getting that guy. And the way we can do that is simply by like saying like 0 times that column, 0 times that column, 2 times that column, 0 times that column, adding them together, and we get that. So we have kind of a basic way of thinking about compositions of functions in the following way, by just thinking of what the ultimate destination of each standard basis element is. Okay, so then as we go along, okay, so we can get a matrix for, we can call it A squared for the matrix A times A. Right. Okay, each row. So this is right. So rows tell us something too, and we already discussed that and talked about what that means. Another way of thinking about this is taking the transpose of a matrix. So this is the adjacency matrix. It's take its transpose. What does that mean? That means to think of this column now as a row. This column now as a row. This column now as a row, and that column now as a row. Notice that okay, that if we do that, what have we done? Well, here a column means things coming into, and that changes to a row, which means things going out from. So basically what it means is we've switched all the directions. So all the arrows of the graph, digraph, have switched. And that happens when you take the adjacency matrix and you take its transpose, then you reverse all the arrow directions. Okay. Now, okay. Let's see, well, what happens if if a matrix is equal to its transpose? That's called symmetry, or being symmetric. So if like this row is equal to that row or that column, so this first row is equal to the first column, second row is equal to the second column, this is equal. Notice that there's a nice symmetry that develops when we say rows like certain positions are the same thing as columns. Because if I draw a line, and let's do that, if we draw a line right down the this four diagonal right here, notice what happens. So we have across it, it's like we have a nice perfect symmetry going down. So that's hence we call that a symmetric matrix. Okay, now if we add the adjacency matrix to its transpose, we end up getting something that is symmetric in and of itself. We kind of force that symmetry, and part of it is kind of like when you take the transpose of a transpose, you get back the matrix. And transpose actually splits nicely across addition of matrices. So if we were to take the transpose of this, we'd end up getting AT plus ATT, just taking the transpose of each part. And this part is just A itself. Notice that AT plus A is the same as A plus AT. So we end up getting a matrix that is like forcing a symmetric matrix just simply by adding A to itself. And what we could do then is see this word undirected graph. Undirected graph, that means a graph that where you don't see any arrows, all right? Because what we're going to do is for a symmetric graph, well, we actually only need to read one half of the adjacency matrix because of the symmetry, and we just draw what we see there. Okay, so we only look at, in fact, we look at the diagonal as well. Okay, so we look at all of that, or if maybe we can draw that a little better. So let's see, we're going to look at just that. All right, just these numbers, and we draw things coming, like this is things coming into vertex 4. We draw these things coming into vertex 4 from like 2 from 4 itself, 1 from 3, and 1 from 1. But notice we don't use arrows because actually we have an arrow going this way and going back. But we're just going to consider we're just going to draw one of them, which is represented in one part of this matrix, and then just don't put any arrows because we understand that we really have an arrow going both directions, like this way and that way for every single edge that we put down. So in this way, this is on a directed graph. This particular one actually has adjacency matrix A plus AT. Notice that we've actually added some things in here, because before we had just one loop, but then adding it to itself, that we got two loops here coming. So there's some differences. However, there's some similarities as well. Okay. And it looks like that's where we end this little subsection. Thanks for watching.